Hi everybody, welcome back once again. Continuing on our chapter 4.5 notes on relative motion and 2D kinematics. We're now at the point where we had talked about position, our change in position or displacement. We related those vectors to average velocity and velocity vectors, and now we're going to take it one step further and relate velocity to acceleration. And as you probably recall, average acceleration over a certain period of time, all right, equals, I'm just going to write what's right up above right there, is our change in velocity over our change in time. All right, so that means if you have a change in velocity written in unit vector notation, all right, so change in something x hat, all right, this is our change in velocity right here. You know, I'll write it like this, something meters per second x hat. Something meters per second x hat, all right, and something meters per second y hat right here. If that's a unit vector that describes change in velocity, then all you need to do to turn it into an acceleration is simply divide it by the change in time. However much time elapses right there. So each of those unit vector components, the x hat and the y hat component, just simply divide each of those by time, and you have, all of a sudden, you have an average acceleration in unit vector notation, x hat and y hat. And we can get this pretty easily by subtracting a final, or taking a final velocity and subtracting the initial velocity from that. We know how to subtract vectors using unit vector notation. We know how to add them too, but these are being subtracted here. So all we need to do is subtract the x hats and subtract the y hats, and we have something that looks like this. Just divide it by our change in time, or our elapsed time, and we then have our average velocity. So the next example, this is going to be 4.5 number 6, I believe, is going to be one-dimensional acceleration, but talking about it with respect to how velocity changes and becomes a change in velocity vector, and how that becomes an average acceleration vector that is applied to a certain object. So that's going to be in this next example coming up. Okay, so here we are on problem 6 of chapter 4.5, and I just have this little note right here. You may have seen it already. I think I recorded this previously under the name of problem 10, so you may have seen it marked 10, but from here on out we're going to mark this as chapter 4.5, number 6. And here we have one-dimensional acceleration, or really deceleration, because we've got a car coming to a stop. All right, now in just a minute I'm going to go to the next slide, and it will have a little more space for me to write, but we got some things that look familiar to us, but we need to start adding them together and doing some math operations on them while they're in unit vector form. Okay? But the one thing right now that we should point out to you is that we have this car moving in this direction right here that is 25 degrees east of south. I mean, that sounds kind of weird, because don't we usually have south of east and north of west and that kind of thing? Well, if you come across this is just a little thing that you need to change. That means that the car is going this direction here. And so if you go south and then 25 degrees east, that would describe that angle right there, 25. However, we don't like that because that's based off the vertical. We don't want an angle based from the vertical. We want it based from the horizontal. So if the other half, or I should say the other, you might say complementary part of that quadrant, if the quadrant is 90 degrees, take 25 away, what would that be? That would be 65 degrees, if I can squeeze that in there. That's what it would be south of east. All right, so it's the same direction. 25 degrees east of south is the same thing as 65 degrees south of east, but this is a more agreeable angle to us right here because it's based off the horizontal. So let's go ahead and change that right now. So that's 65 degrees south of east. All right, just a little logistical thing that I should point out to you. If you ever come across that in the future, don't freak out. Just change it, just basically subtract it from a 90 and you'll get your other angle. So, all right, let's go ahead and let's do this problem right here. I'm going to go to the next slide. All right, so I got a little more room right here. One thing you may be noticing is my dog's barking in the background. Hopefully that's not too loud. If you hear it, that's what's going on. So, all right, we got a car coming to a stop at from some speed. So here's our car. We're going to do a brown car. All right, it's going this direction. All right, and remember it's 65 degrees south of east right here. It has an initial velocity, okay, v initial, and the final velocity, well, it comes to a stop, so that's 0 right there. So that should look familiar to us from problems that we did before in the past. The only thing is we need to do something with this initial velocity and final velocity. All right, so v initial, let's see, I'm going to write it, would be a good place to write that. I'm going to write this over here on the right-hand side, okay? V initial equals what? It's 25 meters per second at what angle? Well, we said it was 65 degrees south of east, okay? And the final velocity, v final, that's 0 meters per second, right? Because it comes to a stop. But it's not turning. The car is still pointing in the same direction. So even though that it doesn't really have any magnitude, we'll give it a direction anyway, just for the sake of argument. All right, 65 degrees south of east. It's still not moving in that direction, but it hasn't turned. So that's the point right here. All right. Now what part A is asking us is find the car's change in velocity. Well, we know change in velocity. Delta V. That's V final minus V initial, right? Well, we're going to subtract V initial from V final, but in order to do that, we need to turn them into unit vectors. Right? We can't subtract, well, you might be able to subtract 25 from 0, but it wouldn't quite work perfectly if you had different values right there. So we need to subtract them by turning them into unit vectors first, okay? So I'm not very organized right here. I'm gonna go back over to the left-hand side, and you know, before I do, give me a second right here, so I can move some of this stuff around. Nope, don't want to do that. I thought maybe I could move around my. Nope, I don't do it that either. Okay. Well, I thought I could move my text around, but I guess I can't because I locked it in place. So I'm just going to write over on the left-hand side. I'm going to convert to. Let's see, I'll convert to blue right here. I'm going to start writing part A. All right, A right there. Now, like I said before, we need these vectors, initial and final velocity, in unit vector notation. So we're going to have to take this 25 meters per second at 65 degrees south of east and turn that into unit vectors. So V initial, I'm kind of doing this backwards right here, is going to be something something x hat plus something something y hat, right? X hat plus something something y hat right here. So what is that? Well, 25 cosine of 65, that gives us 10.6, all right? 10.6 meters per second. Now this is south of east, so it's going this direction right here. So the x should be positive, but the y is going to be negative. So we need to keep track of that. So for the y, we use a sine, right? 25 degrees times the sine of 65. 25 sine 65, I get 22.7, we'll say, okay? But it's going to be negative 22.7 meters per second y hat. All right, that's going to be very important, okay? Especially when it comes to adding and subtracting these. All right, so V final, this is going to be easy, all right? Well, I just wrote 0 in there, but let's write it in unit vector notation. Again, bear with me here because you're going to need to know how to do this, and doing it the long way, or at least watching me do it the long way, is one way to kind of get that in your head. All right, it's going to be something x hat and something y hat right here. Well, I think you know what that's going to be. 0 times anything is 0, so it's going to be the final velocity is 0 meters per second x hat and 0 meters per second y hat right there. That's pretty easy. Okay, now we can actually subtract them. So I'm going to do that in blue for part A. We want to find the car's change in velocity in unit vector notation and in magnitude direction notation. Okay, so delta V right here, change in velocity. I should really be drawing arrows over these. I've been getting lazy. Arrows. These are all vectors, all right? Is going to be V final vector minus V initial. All right, well, let's subtract them using unit vector notation. And I know you're saying in your head, yes, I know what this is going to do, Mr. Miles. It's going to give us the same values because we're subtracting something from 0. Right, but the point here is to practice doing this because you're going to be having other non-zero values later on. All right, so what is it? X hat. It's going to be final minus initial x hat, right? So 0 minus 10.6 x hat. And y hat, what is that going to be? 0 minus negative 22.7 y hat. Okay? All right, so what does that come out to? Our delta V, 0 minus 10.6, okay? So negative 10.6 meters per second x hat, and 0 minus 22, okay? So that's going to be 0 minus negative 22, that's going to be 22.7 meters per second in the y hat direction right here. Okay. Now the one thing you'll notice is this, that this right here, the initial velocity was positive 10.6 meters per second x hat and negative 22.7 meters per second y hat. You'll notice that the change in velocity now, the change in velocity is just the opposite. All right. Because it went from having an initial velocity to nothing. So the change must be opposite, or it must be negative of what the initial values were right here. So that's our change in velocity in unit vector notation. Let's just do some Pythagorean and inverse tangent and turn that into magnitude and direction. So delta V, magnitude, delta V is going to be square root of, what is it, negative 10.6 squared plus 22.7 squared. That gives us 10.6 squared plus 22.7 squared to the square root. Lo and behold, that's 25. Oh my goodness. You knew that, right? Because it was being subtracted from 0. But it's 25 meters per second at what direction? All right, that's the direction part right here. So it's inverse tangent of what? The y over the x. So 22.7 divided by 10.6. Remember we use absolute values right here. So inverse tangent 22.7 divided by 10.6. 65 degrees. Wow. Didn't see that coming, right? Of course you did, because this is all on a straight line. It's all in one dimension. Okay, at 65 degrees, what of what? Now this is going to be interesting because, look, our signs have changed. Okay, we've got a negative x and we've got a positive y. So instead of south of east like we had before, south of east is going like that. A negative x and a positive y is going to be going the opposite direction, right? Negative x and positive y, so that's north of west right here. So our change in velocity is going to be directed in the opposite direction as the initial velocity. In this case, especially because it's slowing down. All right? Slowing down means that it's decreasing its velocity, so the change in velocity is acting in the opposite direction. What I'm going to do for the sake of time is I'm going to stop right here, and I'm going to pick up with parts B and C in this problem in subsequent videos. So thanks for following along so far, and I'll see you in the next one.